In ensemble theory, till now we have learnt about the two important ensembles. First of all, you have seen the concept of microcanonical ensemble, and secondly, we have discussed the canonical ensemble. Okay. Now, finally, from today, we will learn about the third and the most important ensemble, which is called grand canonical ensemble. Okay. Although I have discussed the ensemble theory just as an overview in my first lecture, and in that lecture you have learnt about all the three ensembles, but in elementary way. Now we are discussing in these ensembles separately in detail. So here in a series of lecture you will find the almost all concepts regarding this grand canonical ensemble. But there is a common question which definitely have been arised in your mind, that why we study these three types of ensembles, or in other words you can say definitely we have the thought that why when we learn about the microcanonical ensemble, then what is the need of canonical ensemble and the grand canonical ensemble? What is its need? Why these ensembles are needed? It is obvious. The answer of the question will be obvious. Definitely, there will be some shortcoming or drawbacks of the previous ensembles, which has been rectified, which has been removed in this ensemble, because you know that any new theory comes when there is a shortcoming, there is a drawback in the old theory. So you can thought that definitely there will be some trouble, some drawback, some shortcoming of the canonical ensemble and the microcanonical ensemble, and all those drawbacks have been removed in this grand canonical ensemble. This is obvious. So in my first lecture on grand canonical ensemble, I am just introducing you what is this grand canonical ensemble and why it is needed. Okay. Actually, after this introductory lecture, we will learn about the concepts of this grand canonical ensemble. But today, I am just introducing you what is this grand canonical ensemble and why we need this grand canonical ensemble. So I have written here, you can see why grand canonical ensemble, why you need it. Okay. Actually, to get the answer of this very question, I am just bringing you some back. Let us consider here, see this figure, that this larger square or rectangle, let us consider represents an isolated system. When you say an isolated system, what does it mean? It means this system will not exchange either energy or the particles with its surroundings. Okay? And you know, if a system does not exchange energy and particle with its surrounding, then the system is called isolated. And that isolated system is also called microcanonical ensemble. Okay? So you can say that if we mark this bigger square or rectangle by M, this M is nothing, this is simply an isolated system or a microcanonical ensemble. It means for this M, the total energy is constant because it does not exchange energy with its surrounding, and the total number of particles N in this system is also constant. So this is just a microcanonical ensemble or an isolated system, you can say. Now let us consider that this SS, which has been marked by a small rectangle here, this S is just a part of this isolated system, and we will call it subsystem. This S will be called subsystem. Okay. Then, as you know, in case of an isolated system or microcanonical ensemble, what were the set of three quantities or the set of independent variables? In describing the microcanonical ensemble, you have learned that in case of microcanonical ensemble, the three independent variables was E, V, and N. It means in case of a microcanonical ensemble, we know that energy remains constant, volume remains constant, and number of particle also remains constant. Okay? But can you think that how energy of a system will be constant? As I have told you earlier, for keeping the energy at a constant value, that is, our system will not exchange energy with its surrounding, it is necessary to keep the system inside a vessel, uh, inside a container whose walls are perfectly non-conducting or perfectly insulating. Okay? But as you know, that this perfect word or ideal word is just theoretical. Actually, there will be no such a container which will not allow any exchange of energy. Some amount of energy will be definitely exchanged, because to keep the energy at a constant value is a trouble process, is very hard practically. Practically it is not possible, because none of the container will be perfectly non-conducting. So there will be some exchange of energy. So when you say that in case of microcanonical ensemble, energy remains constant, that is just an ideal situation. In practice, it is found that there is some exchange of energy. So this was a problem with the microcanonical ensemble, or you can say that practically to keep the energy constant is troublesome. It is a hard work. Okay, or in other words, you can say that to keep the energy a constant at a particular value, as we assume in case of microcanonical ensemble, that is not practically feasible, practically possible. Okay, so people thought about an ensemble which will allow energy to be exchanged. Okay, the restriction on the constancy of energy was relaxed, and you know, when energy will exchange, but to keep the temperature at a particular value is practically easier process. So the second ensemble was thought, and which is called actually canonical ensemble. And you know, in case of canonical ensemble, the independent variables are not E, V, and N. These are the independent variables of microcanonical ensemble. Okay? But as I have told you, that to keep energy at a constant value is somewhat troublesome. It is not practically feasible in ideal situation, ideally. So, instead of E in canonical ensemble, temperature was used. So the independent variables in case of canonical ensembles are T, V, and N. Okay, T, V, and N. These are the independent variables in case of canonical ensemble, and you have learnt it earlier. Okay. So in case of canonical ensemble, there will be an exchange of energy between the subsystem and the reservoir, or you can say between the system and its surrounding. Okay. But in this ensemble too, the number of particle remains constant. There is no exchange of particle between the system and its surrounding in case of canonical ensemble too. Okay. Actually, what I have just explained, I have mentioned it here in brief, and I am just giving a reading for your convenience. You can see. I have written that in micro-canonical ensemble, the independent variables are what? These are E, V and N. Okay. Now, E equal to constant, this fact implies that system is isolated. Okay. System is isolated. But to keep E constant is not practically feasible. Instead of E, to keep the temperature T constant is practically convenient. Constancy to maintain the constancy of temperature is practically convenient. And that's why I have told you that in a canonical ensemble, the variable E changes to T. And in this ensemble, the independent variables are what? These are T, V and N. Okay? T, V and N. Now, as in canonical ensemble, the independent variables are T, V and N. So N, which represents the number of particles, that remains constant. But you can think that in practice, in our nature, there are so many processes in which the number of particles N does not remain constant. You can remember, you have definitely studied chemistry, and you know in a chemical process, in general, the number of particles changes. For example, if you consider that there is KClO3, this is potassium chlorate, and you know when it is heated, this potassium chlorate will be when heated, then we get in fact KCl, potassium chloride, and oxygen, O2. Actually here you can multiply it by 2 and here will be 2 KCl and 3 O2. Now see, there was only 2 molecules of potassium chlorate, okay? And in the reactant, but in the product you can see that there are 2 molecules of potassium chloride and 3 molecules of oxygen. So in product there are 5 molecules, but in the reactant there was only 2 molecules. So there is a change in number. Okay, this is a chemical process. So I have told you that in chemical process, in general, the number of particles change. Okay. At the same time, you can also think about quantum processes. Quantum processes. In quantum processes too, the number of particles does not remain constant. There are several examples, and definitely you have an idea of it. You know that when electromagnetic radiation falls on the surface of a metal, photoelectric effect takes place. You know it. This is a metallic surface, okay? And this EM radiation of energy h nu is incident on it. And you know, from this metallic surface, an electron is emitted, and this process is called what? This process is called photoelectric effect. But do you know what will happen to the fate of this photon which strikes the metallic surface? Actually, the photon gets absorbed, it gets destroyed, it becomes existenceless. When the photon strikes the metal surface, it loses its total energy and it gets disappeared, and electron is emitted. So in this process of photoelectric effect, there is just an annihilation, thus just an destruction of photon. So number of photon will decrease. Okay. On the other hand, when you produce X-ray, then you strike the beam of accelerated electrons on a metallic surface, and X-ray photons are produced. So in that process of production of X-ray, there was no photon before the strike of electron on the metallic surface. But when the accelerated beam of electron strikes the metallic surface, photons are created. So X-ray is production of photon, and photoelectric effect is destruction of photon. Okay. Similarly, there is a very famous process of which is called pair production. In pair production, a photon gets destroyed and we get a pair of an electron and a positron. Okay, and this photon actually gets destroyed. And in annihilation, when electron and positron collide, then we get photon. So during annihilation, these electrons and proton electron and the positron get destroyed and photons are produced. So in a simple way, you can say that in a quantum process, the number of particles does not remain constant. I have given some example here, particularly regarding this photon, that during a quantum process, the number of photons do not remain constant. These photons may be created or these may be annihilated. Okay. So to keep n constant is not possible, particularly in chemical processes and in quantum mechanical processes. So people again felt a necessity of such an ensemble which will allow the number of particles to be exchanged. Along with the exchange of energy, the ensemble should also exchange the number of particles. Such ensemble was needed. Actually, such an ensemble which allows the exchange of energy as well as the number of particles, that is called actually the grand canonical ensemble. Okay, I think you are getting the things. Actually, what I have mentioned here, I have written for your convenience. You can see in short all those things I have mentioned here. There are processes in which the number of particles n does not remain constant. For example, chemical processes, quantum processes. Okay, you can see. In quantum process, the particles like photons are created and annihilated, as I have told you. And I have also given some example, although I have not written all those examples here, but I have mentioned and I think you have understand those. Okay. So since in chemical processes and quantum mechanical processes, number of particles do not remain constant, so definitely there is a need of an ensemble which allows the subsystem to exchange the energy as well as particles with the remainder of the system, that is the reservoir. Okay, and such an ensemble is called grand canonical ensemble. So I have defined the grand canonical ensemble here. You can see the ensemble which allows subsystem to exchange energy as well as particles with the reservoir is called what? It is called grand canonical ensemble. Okay. Actually here now n will change. So definitely the set of three variables for this ensemble will be what? As you know, in canonical ensemble, the independent variables are T, V and N. Okay. But in case of grand canonical ensemble, since N also changes, so instead of N, we have to use here the new variable. And what is that new variable? That new variable is actually called, is denoted by the symbol mu, and it is simply the chemical potential per particle. Chemical potential per particle. And so you can say, in case of a grand canonical ensemble, the independent variables are T, V and mu. Okay. These are the independent variables in case of grand canonical ensemble. Okay. Now, since in this case particle changes and we have used the chemical potential in at the place of number of particles n. So in this case, instead of free energy, which is also called Helmholtz free energy function, and you define the free energy function f by u minus ts, u minus ts. Instead of this f, in grand canonical ensemble, we use a potential which is called grand potential. Instead of f, you have seen that in calculation of canonical ensemble, we always talk about this free energy function. But at the place of f, in the case of grand canonical ensemble, we will use grand potential, and that grand potential is defined like this. This is denoted by this capital omega, and it is defined by f minus mu n. Here mu is the chemical potential per particle. Okay. Actually, you have to subtract this value mu n from f. Okay, and then you will get the grand potential. But as f is equal to u minus ts, so you can say that omega is equal to u minus ts minus mu n. Actually, this grand potential is minimal when this t, v and mu are held fixed. In fact, in that condition, this omega will have a minimum value and our system will be in equilibrium. Okay. So now see this figure here, which I have drawn in the first page. You can see this figure. Actually, as I have told you earlier, that this bigger rectangle represents an isolated system, or you can say that this is a microcanonical ensemble. And we have taken here a very small part of this microcanonical ensemble, which is called subsystem. Okay? And the remaining part of this isolated system has been marked by R, and this is called reservoir. So, in case of grand canonical ensemble, what will happen? This subsystem will exchange energy with the reservoir. There will be an exchange of energy. And apart from the exchange of energy, this subsystem will also exchange the number of particles with the reservoir. Okay? So in this case, this subsystem is exchanging energy with R, and this subsystem is also exchanging number of particles with R. Okay? With R. So you can say that R, which represents the reservoir, and S, which represents the subsystem, when these two will be added, that will be equal to the isolated system. This is equal to isolated system, or you can say this is microcanonical ensemble. Microcanonical ensemble. Okay? Microcanonical ensemble. So microcanonical ensemble is simply equal to the composition of the reservoir and the subsystem, between which there will be an exchange of particle and the energy. But the total number of particles and the total energy will remain constant. Okay? Energy of this subsystem may decrease or increase because it may send energy from it to the reservoir, or it may gain energy from the reservoir. Similarly, the particle may flow from the subsystem to the reservoir, or it may flow from reservoir to the subsystem. But as there will be no creation or no destruction of particle at all, so the total number of particle and total energy will remain constant for this isolated system. Okay, when you say total, that means the total number of particle of the isolated system or the microcanonical ensemble. Okay, So I think you have clearly understand why canonical ensemble was needed. The uh, because in microcanonical ensemble we say that energy remains constant, but to keep the energy at a particular value, at a constant value, is troublesome. So instead of E, in case of canonical ensemble we use T, that is temperature, as an independent variable. Okay, and to allow the number of particles to be exchanged between the subsystem and the reservoir, we need the another ensemble which is called grand canonical ensemble, in which case there will be an exchange of energy as well as the particle. Okay, and this is why we need a grand canonical ensemble. So this was a very short lecture on just introduction of grand canonical ensemble. But in the next lecture, we will learn about the basic concept of this grand canonical ensemble, and that will be for finding the probability distribution function or Gibbs distribution function and partition function for this grand canonical ensemble. Actually, you know, all calculations related to this grand canonical ensemble will be in terms of the partition function. So the second lecture will be most important, and I hope you will definitely watch the second lecture too after watching this first lecture. Okay, so thank you very much.